In this lesson, we'll be discussing the third type of conic section called a hyperbola. Now remember, the first type of conic section was a circle. The second type was an ellipse. And now we're going to see that the hyperbola, although it looks drastically different from both of those, the way that we graph will be very similar to the way that we graphed an ellipse. So a hyperbola is the set of all points, for instance, this point on the graph over here, that's going to be a fixed difference between the two foci. Now remember, for an ellipse, if these 2 points here, these red points were the vertices, then the focus, or the foci, both focuses, would be on the inside of the vertices. Now we see that these foci are actually going to be on the outside of the vertices, but now they'll be inside of these curves referred to as the hyperbola. Now what we should recognize is that hyperbolas, unlike circles and ellipses, have slanted asymptotes that this red graph is going to get close to as it extends out to positive infinity and negative infinity. Now if we take a look at the definition of what creates a hyperbola, then it relates very similar to what we did for an ellipse, where in an ellipse, we said that every point on that ellipse was the same distance from each of those foci. So the sum of the distances was always the same. Well, now we're going to look at any point on the hyperbola and recognize that the difference in the distances will always be the same. What does that mean exactly? It means that if we take the smaller distance from the focus to that point and take it away from the other side, then we're going to be left with this yellow strip that apparently is always going to be the same no matter where we go. And not only that, that strip should always be equal to the distance between the vertices. We could even see that if we pick another point on the opposite side. Notice that when I draw the distance to the first focus, it's smaller. So if I take that distance away from the other side, we're left with, again, this distance, which will always be the distance between vertices. Now, if we look at the types of hyperbolas in the equations, the standard form of a hyperbola will look very similar to that of an ellipse. You should notice the only difference is that there's a minus sign in between the two variables. So sometimes the x term comes first and therefore is positive. Sometimes the y term comes first and therefore it's positive. So if the x term comes first, then we know that this graph will open left and right, very similar to this graph here. But if the y term comes first and therefore the x term is negative, now it's going to be opening along the y-axis and therefore opening up and down. So let's go through the process of finding our x and y intercepts in order to get a better idea about why these graphs look the way they do. So if we take a look at x-intercepts, remember that we set the y values equal to 0, which will cancel the term involving y. So that leaves us with a single fraction with x, which means if we cross multiply, we get x squared equals a squared for this first equation. But if the x squared term was the negative term, now notice when we cross multiply, we get that x squared is equal to negative b squared. When I take the square root over here, we get that negative a and positive a are going to be our x-intercepts because the square root of a squared is plus or minus a. But that would make sense because notice that there are points on the x-axis. While over here, there are no points on the x-axis. So there shouldn't be any x-intercepts, and we can see why, because notice that x squared can never be negative. So let's look at how similar this is to the y-intercepts, where we set x equal to 0, which will cancel the term involving x. Now notice that by cross-multiplying here, this now becomes y squared equals negative b squared, while this over here becomes y squared equals a squared. So what we're seeing here is that since y squared can never be negative, this shows that there are in fact no y-intercepts now. But that should make sense because if we're looking at this equation, we know that since x comes first, it's opening left and right, so there will be x-intercepts, but there's a gap in between the two branches of the hyperbola, so there shouldn't be any y-intercepts. As opposed to this graph over here, we already determined that there were no x-intercepts, but now we should see that the y-intercepts are at negative a and positive a, which is why we see y-intercepts here. So if we now just look at the results of what we found, notice that the x-intercepts are at a, while for this equation, the y-intercepts are at a and negative a, or rather a units away from the center. So notice that the value of b, it doesn't appear that we actually used it like we would have done to find covertices for an ellipse. But it turns out that the b value is used in order to find the slant asymptotes, which we'll see in this next example. So notice that this is, in fact, a hyperbola. And we can see that because of the fact that the x squared term and y squared terms are being subtracted. But it's not in the standard form because it's not equal to 1. So the first step here is to divide by 144. And now we can cancel out common factors in the numerator and denominator to get this result. Now notice that 9 is 3 squared and 16 is 4 squared. So we can now see what our values of a and b are. Now for an ellipse, we defined a to always be the larger value. But notice that doesn't necessarily need to be true for a hyperbola because all this a value is describing is where to put our intercepts or where to put our vertices. So notice that since this hyperbola opens left and right, because the first term involves x, we can now pretty easily find our center and our vertices. So our center is 0, 0 because there is nothing being subtracted from x or y directly. And because it opens left and right, we could see that this value of 3 indicates how far away from the center I should be plotting my vertices. The next step is to find my slanted asymptotes. But in order to do that, we've got to realize that b has not yet been used. And we're not going to plot points at -4 and +4, which are our b values. But we are going to use those in order to find our asymptotes, because remember, lines have particular slopes. And to find the slope, we're taking the rise over the run, which is always the change in the y direction compared to the change in the x direction. So these values of 3 and 4 indicate what the rise and run will be. Since 4 is attached to y, then 4 indicates the rise. Since 3 is attached to x, 3 indicates the run. So notice that for my formula for the slopes, it's simply plus or minus b over a, and therefore my slope is +4/3, which means from the center, rise 4 and run 3, and -4/3, which would mean drop 4 and run 3, which is why there are two different asymptotes, one with the positive slope and one with the negative slope. Turns out that I've got everything I need in order to graph this hyperbola now. We plotted our vertices, which are the points where the hyperbola starts, and now I simply curve to each of the slanted asymptotes, and that's my hyperbola. The way I like to graph this is to start my pencil at the vertex and curve upwards towards the slant asymptote. And then I come back to the vertex and curve down to the asymptote. Then I go to the other side, plot my vertex, curve up to the top asymptote, come back to my vertex and curve down to the bottom asymptote. Now there is one more important aspect of this graph that we discussed at the first slide when we were describing the difference in the distances. We said that there are 2 points inside of this hyperbola known as the foci. Here we can see that the foci occur at -5 and 5, but why? Where did we get those foci? So let's go ahead and derive a formula to see how we can actually find the foci. So notice that the standard form of a hyperbola that has a center at hk is going to be as follows here. When we end up looking at this equation, notice the only difference is that the h and k are being subtracted from x and y. And so what this does is it moves the center somewhere other than the origin. But the way that we graph is going to be exactly the same process as we just did on the prior example. Notice that first of all, the center is going to be at +1 and -2. Now notice that some people would often mistake the center by saying -2, +1, because they're simply going in order of what the equation says. But remember that h is the difference in the x coordinate and k is the difference in the y coordinate. So we plot our new center. And now I should realize that 16 is actually 4 squared and 4 is actually 2 squared. So because y comes first, I know that this is going to be opening upwards and downwards. So I'm going to be moving 4 units in the direction of y. So I'm just simply going to move 4 units upwards to find my first vertex and 4 units downward to find my second vertex. So when I plot those points, notice that the x coordinate of 1 doesn't change. I'm just simply adding 4 to the -2, and I'm subtracting 4 from the -2. And now these are going to be the vertices, or the highest and lowest points of my hyperbola. So we now need to find our asymptotes, but notice that we haven't used 2 yet. And that's because that's going to be used in order to account for our rise and our run. So notice that the rise is the change in the y direction, while the run is the change in the x direction. Here we can see that 4 is attached to y, so 4 is actually our run, or our rise rather. So 4 is attached to y, so that's our rise. While here, 2 is attached to x, so that's our run. So notice that the formula for the slopes of the asymptotes is not always b over a. Sometimes it's a over b, depending on which one indicates the rise and which indicates the run. So here we could see that the slope is ±4 over 2, which is really just ±2. So from our center, we can now rise 2 and run 1 in order to create our first asymptote. Go back to our center and we can go in the opposite direction now. Rise -2 and run 1, which now allows us to create our second asymptote. And now we've got everything we need in order to graph our hyperbola, because the red points indicate the vertices. We curve towards our slant asymptotes, and there will always be a gap between the 2 branches. But we still don't know how to find those foci. So let's take a look at the standard form of our hyperbola here. And we're going to take a look at the graph of the first equation that we graphed. Notice that because it's opening left and right, that means that x is coming first. So this standard form indicates x squared over a squared, where the a value is telling us where the vertices are. Now what we're going to do in order to come up with a formula to find this focus distance is that we're going to zoom in on just one small piece of the graph. And so now we're going to take a look at that piece, recognizing that the center is this green dot. And now we can see that the red dot is our vertex of our hyperbola, and this yellow dot is going to be called our focus. Now notice that in order to find the slope of this asymptote, we simply did the rise over the run. Now notice that the run is what's attached to x, so that's our a value. The rise is what's attached to y, that's our b value. So now in this particular problem, the distance of this vertex is a, the distance up in order to create our asymptote is b. We want to know the distance to the focus, which we're referring to as c. Now what's interesting about this value of c is that it turns out to also be the hypotenuse of this indicated triangle. So we now have this triangle where we can use the Pythagorean theorem again in order to find the value of c. So we should realize that a squared plus b squared is equal to the hypotenuse squared. And therefore, we've got an equation that involves the values underneath the x and the y, which are a and b, but it also involves the c value, which is what we needed. So we can now take the square root of both sides and find out that the c value can be found by taking the square root of a squared plus b squared. You may remember that the formula for finding the focus of an ellipse was exactly the same, except that it had a minus sign in between. Now for a hyperbola, we're using the standard Pythagorean theorem, and therefore it has a plus sign. We'd also like to take a look at something referred to as the eccentricity of a hyperbola. You should realize that for one of these hyperbolas, the one on the left here, that it appears to be more stretched out vertically here. And in doing so, we can recognize that these foci are further away from the vertex. But when I seem to smash those asymptotes together, it looks like it forces that focus to get closer to the vertex. We refer to this as the eccentricity of the hyperbola, or we're going to use the variable e. Now, the eccentricity for a hyperbola is always going to be a number greater than 1. And this describes basically how close the foci are to the vertices. So just like we did with an ellipse, we're going to think of the eccentricity as a percentage of how big c is compared to a. And we're going to use the exact same formula that we did before. If this distance right here is a, between the center and the vertex, and the distance from the center to the focus is c, then the eccentricity is simply the ratio between c and a, or rather what is c divided by a. So notice that in this particular problem, or in all hyperbolas rather, the eccentricity is bigger than 1 because c is always outside of wherever the a value is, because it's inside of the curves. So since c is always larger, then this fraction will always be bigger than 1. So this will be considered a larger eccentricity since c is not very close to a, but this here will be a smaller eccentricity and therefore closer to 1 because c is in fact close to a. So we're going to revisit this exact same first equation that we had and the exact same graph that we had before. We didn't know before how to find these foci, but we already found our vertices and our asymptotes. Now we'd like to use the formula for finding the foci, which is c equals the square root of a squared plus b squared. Well, remember a squared plus b squared is nothing more than just the denominators of x and y. So we're taking the square root of 9 plus 16, which is nothing more than the square root of 25. So that's why the c value is 5, which tells us how far to plot my focus from the center. So since the center is at 0, 0, I know that I'm going to be plotting one focus at 5, 0, and the other focus at negative 5, 0. Now for the eccentricity. The eccentricity, remember, has our formula of c over a, and since we now know that our distance of c is 5, and our distance for a, the vertex, is 3, then we're making a comparison between the c value and the a value. And notice because the numerator is larger than the denominator, this value is greater than 1. The closer this focus is to the vertex, the closer the eccentricity will be to 1. So this is how we can now graph all hyperbolas, but I'd like you to really recognize the similarities to how we graphed an ellipse. So now let's take just a quick look at how to recognize all of the different conic sections based off of their equation. So here we see 4 different equations, or rather 4 different conic section equations. And these are all in expanded or general form, as we saw with a circle and an ellipse. And so what we're going to take a look at now is how can we look at the shape of these equations and know what the shape of the graph is going to be. Let's take a look at this first one. The first one is going to be a circle. And it's a circle because of the fact that both of these terms, the x squared and the y squared, are positive, and they both have the same coefficients, which means that in the x and y directions, it's going to be stretched the exact same distance, which is what makes it a circle with a radius of r. Now let's take a look at the second equation here and realize that the x squared and y squared terms are being subtracted. That automatically indicates that this is a hyperbola because the x squared term is positive and the y squared term is negative. But now you look down here and realize that again, you see an x squared and a y squared term, but there's a plus sign in between. So that means that it's not a hyperbola, but maybe it's a circle because that's what happened with circles as well. However, the different coefficients in front of x and y tell me that it's an ellipse because it's going to be spread different amounts in the different directions. So since the coefficients are different, I know that this forms an ellipse. And now we'll take a look at the x squared and y squared terms in this equation, but we should realize now that there is no y squared term. Only one of the terms, only one of the variables is being squared, which tells me that it's none of the above. This is going to be the last conic section that we learn, referred to as a parabola. Now remember, parabolas are graphs of quadratic functions, and quadratic functions look like y equals x squared. Well, notice that I have an x squared term and I have a y term. But sometimes now the y will be the variable being squared, which is why sometimes the parabolas that we learn in terms of conic sections will be opening up and down like our regular quadratic functions, but sometimes now they'll be opening left and right. So the reason we know this is a parabola is simply because only one of the variables is being squared.